So this video today is going to focus on our first learning target for our third unit, which is analyzing the difference between mass and weight. And today we're going to learn how to define mass and weight. So the first thing I need you to do is take out your blue unit organizer and in slot 2, write in mass versus weight notes. And as usual, notes have no score attached to them. And in the third slot, I need you to write down IP, Newton's law of gravitation. And that'll be worth 10 points. Find this note sheet. This is going to be page 2. Now, the differences between mass and weight are pretty easy to distinguish once you know them. But in America, we use those two things really interchangeably. So the definition of mass is the amount of matter in an object. And that's measured in either grams or kilograms. And we measure it using a balance, like those triple beam balances, or a scale, like a bathroom scale or the scale you hop on at the doctor's office. Now the definition of weight is the gravitational pull on an object's mass. And weight is a force, so we're going to measure it in newtons. Now in the English system, we say pounds. And there's actually a conversion factor between pounds and newtons. 1 newton is equal to a quarter pound. So maybe one day you could go to McDonald's and order a Newton burger instead of a quarter pounder. And if you do that, you should take video so I can see it. Now because weight is a force and it's measured in newtons, we denote weight as the force due to gravity, or a big W for weight. Either of those are correct. We measure weight either using a spring scale, or we can do math, where the force due to gravity, or weight, is equal to the mass of the object times the gravitational pull of your location. Now, the next part, seeing if mass and weight are constant, that's where this gets pretty tricky. Mass is always constant because the amount of matter doesn't change. But weight is not constant. It depends on the gravitational pull of where you are. So let's take this example. I have a mass of 52 kilograms. My mass is never going to change. How much I weigh on Earth is going to be different than how much I weigh on the moon. So I'm going to weigh less on the moon because there's less of a gravitational pull. But my mass, the amount of matter in my body, doesn't change. So my mass stays the same, but my weight changes. Now, gravity is an attractive force on Earth between all objects on the universe. And gravity isn't just on Earth or objects near the Earth, it's everywhere in the universe. Weight, we just talked about above, is a way to measure the gravitational pull on an object's mass. And when we talk about gravity, we can either be talking about the gravitational force of weight, or we can talk about gravity as an acceleration of 9.8 meters per second squared. This number is only the gravity on Earth. So Newton had a law of universal gravitation, and this doesn't fit into his law of motion. And Newton's law of universal gravitation states that the gravitational attraction or the gravitational pull between two objects depends on two things. One is the masses of the objects. The higher the mass of the objects, the stronger the gravitational attraction. So the bigger the objects, the more attracted they'll be to each other. So gravitational force and mass have a direct relationship. If one goes up, so does the other. Or if one goes down, the other one goes down too. An example is that Jupiter, which is the biggest planet, so it has the biggest mass, has the most moons. Because it's so big and so massive, it attracts all these things to it. Another example is the Sun, which is the biggest star in our solar system. All the planets orbit it. So because the Sun is so massive, it allows, that mass makes everything kind of rotate around it. Now, the distances between objects is the other thing that Newton's law of universal gravitation depends on. So the smaller the distance between the objects, this is just a really long way of saying the closer the objects, the stronger the gravitational attraction. So gravitational force and distance have an indirect relationship. And our example for this is that Mercury, which is the first planet closest to the Sun, and the Sun will have a stronger gravitational attraction than Pluto and the Sun, which is the planet farthest away from the Sun. After you watch this video, you should get an independent practice about Newton's law of universal gravitation. Hopefully you'll finish this in class so then we can move on to the next thing.